In this video, I want to describe what a coefficient is in a balanced chemical equation. So we have a balanced chemical equation, and either you balanced it yourself or maybe it was given to you already balanced, and we want to know what the heck these numbers in front of the molecules represent. And in the way that I've described balancing chemical equations, I've drawn out the molecules like so, and you might say, well, they represent the number of molecules for each of these respective compounds. And that's totally and absolutely correct interpretation of what these coefficients mean. So here we have one and 2. No number written means that there's 1. So 1 and 2 because I have 1 N2 molecule. Or 3 H2s because I have 3 H2 molecules. Or 2 NH3s because I have 2 NH3 molecules. So that is one completely correct interpretation of what these coefficients represent. It could be the number of molecules of each of the compounds given. The number of each individual molecule. It could also represent the number of dozens of each of these compounds. So here I have 1 dozen N2 molecules. Or here I have 3 dozen H2 molecules, so 36 total. Or here I have 2 dozen NH3 molecules, or 24 total. So that's another totally correct interpretation of what the coefficients represent. Another much more common representation of what the coefficients represent is a mole. So here, since I have 1 N2, that could mean that I have 1 mole of N2. And then a 3 here represents that I have 3 moles of H2. And this 2 here could mean that I have 2 moles of NH3. So as long as the unit of measurements that we're using is consistent across all of the molecules, then it doesn't matter what descriptor of how many we use. So we could say that they're each individual thing. We could say that there's a dozen. We could say that there's a mole, which means 6.02 times 10 to the 23rd particles of each substance. All are completely valid. This mole, I would say that the mole is probably the by far the most common representation of what these coefficients represent, but they could mean anything. So, but really the most useful way to think about it is to say, hey, it doesn't matter what descriptor we're using for what number of each thing is. What's really most important is the ratios between each thing. So here I have written that there is 1 mole of N2 for every 3 moles of H2. Because there's a 1:3 ratio, for every 1 N2 that we need 3 H2s. Or we could write it vice versa. We could say for every 3 moles of H2, we need 1 mole of N2. All right, or we could write all the other ratios. There's other ratios that we pull out of this. We could say for every 1 mole of N2 that goes into the reaction, we're going to produce 2 moles of NH3. So if I put 1 mole of N2 into the reaction, I'm going to get out 2 moles of NH3. Or we could flip it and say that there are going to be 2 moles of NH3 produced when we have 1 mole of N2 used in the reaction. Lastly, the last ratio we could pull out of this, we could say that there are 3 moles of H2 put into the reaction for every 2 moles of NH3 that we get out of the reaction. Or the reciprocal of that, we could say there are 2 moles of NH3 that are going to be produced for every 3 moles of H2 that are put into the reaction. So all of these are correct interpretations of what these coefficients mean. They're really most commonly referred to the number of moles of each thing. But another common interpretation is the number of molecules, and that's why it was completely correct when I was drawing out the number of molecules as shown here, just like when I was explaining how to balance the chemical equations. But really, I think the most important way to think about it is to think of it really as one thing compared to the other thing. So for every 1 mole of N2 there are that's put into the reaction, there's going to be 2 moles of NH3 that are going to be produced. And so that's going to be really helpful when we're solving problems where I might give you the amount of one thing and then ask you for the amount of another thing that's going to be produced.